hydrocarbon lesson we'll discuss. In this first alkanes, I will explain to you. So, first, while going to this topic, what is hydrocarbon? Hydrocarbon mean compounds which are made up of hydrogen and carbon. Compounds which are made up of hydrogen and carbon are called hydrocarbons. Okay, those are what are those? Alkanes, alkenes, alkynes, and aromatic compounds. These are generally made up of hydrogen and carbon. Alkanes, if you take it, between alkanes, only single bond will be there. So that means any compound, if you take it, between carbon atoms, only single bond is there means generally we can consider those as alkanes. Hmm. And example, if you take it, so here propane is given here. Propane, carbon bond, carbon bond, carbon. Here only single bonds are there. So it is example for alkenes. And alkenes, if you take it, between carbon atom, double bond will be there. And like this double bond is there means those are called alkenes. Example is given here propene. And next, if you take it, what is that? Triple bond, alkynes. Between carbon atoms, triple bond is there means. So those are called alkynes. Example, what is given here? Propane is given. The first propane, next one is propene, after that propane. And next, if you take in benzene ring, any compound contain benzene ring, generally we can call those are aromatic compounds. For the topics we'll discuss about this, the benzene ring here, this one. Okay, so in the benzene, any compound contain benzene ring, those we can call aromatic compounds. Example here it is given ethyl benzene. So first now we're discussing about alkanes. So about alkanes introduction we'll discuss. Introduction we'll discuss so alkanes. So in these alkanes are paraffins. Alkanes are also called paraffins here. Ah, so these are saturated hydrocarbons. These are what are those? Saturated hydrocarbons. Alkanes are saturated hydrocarbons. And naturally, these alkanes occur from what is that mineral oils or petroleum. Mineral oils are petroleum. So these alkanes are called paraffins. Paraffins means what are those? Less reactive alkanes, less reactive substance. Less reactive substance. General formula. We know that general formula of alkanes is what is it here? CnH2n plus 2. CnH2n plus 2. Okay. And hydrocarbons, hybridization, about hybridization, if we discuss, the first hydrocarbon, that means alkanes hydrocarbon is methane, CH4. So in this, carbon is forming four bonds. In this, carbon is forming four bonds. So like that, when it is forming four bonds, carbon, when it is forming four bonds, here four bond pairs. Here four bond pairs are there. There is no lone pair. Four bond pairs means sp3 hybridization. Sp3 hybridization, four lone pairs. So that shape is what is it here? Tetrahedral shape. Sp3 hybridization. Okay, no bond pairs, only lone pairs. That shape is what is the tetrahedral shape. In the tetrahedral, bond angle is 109 degree 28 minutes. 109 degree 28 minutes. Okay, number of bond angles in methane are 6 we'll get it. How we'll get 6? Between this is 1, this is 2, here 3 you can take it. Huh? So next, okay, 4, 5, and this is 6. So like that, 6 bond angles we are getting. Understand how many bond angles we got it? Number of bond angles in methane are 6, while in ethane are 12 we are getting. And bond length, carbon-carbon bond length is 1.54 angstrom. Carbon-hydrogen bond length is 1.11 angstrom. Okay, so these are generally introduction about introduction of alkanes here. Now we'll discuss about preparation of alkanes. Preparation of alkanes we'll discuss. Preparation of alkanes from aldehydes and ketones. From what are those? Aldehydes and ketones. So to prepare alkanes from aldehydes and ketones, two well-known famous named reactions are there. Those are Clemmensen reduction and Wolff-Kishner reduction. Clemmensen reduction, Wolff-Kishner reduction. Clemmensen reduction and Wolff-Kishner reduction, both reductions, we will convert aldehydes and ketones to hydrocarbon. That means alkanes. Okay, aldehydes, ketones converted into alkanes. But in that Clemmensen reduction, it is acidic medium. Here, what we are using reagent means zinc amalgam. Okay, concentrated HCl we'll use. Concentrated HCl and Wolff-Kishner reduction if we use. In this, what we are using that means hydrazine. Hydrazine, NH2 bond, NH2 hydrazine and base, KOH base we'll use and ethylene glycol. Ethylene glycol. Ethylene glycol. So like that, these substance we are using. Okay, so Clemmensen reduction is okay. Clemmensen reduction when you take in this one is acidic medium. This one acidic medium, and Wolff-Kishner reduction when you take it, this one is basic medium. Basic medium. Understand? So Clemmensen reduction, when we don't use that Clemmensen reduction when that reactant is more sensitive towards acids, more sensitive towards acids. Okay, so later I will explain after explanation of these two. In this, what is given here? In this, mainly most commonly used to convert acyl benzene to alkyl benzene. So in this case, this carbonyl group is converted into methylene group CH2 in the presence of zinc amalgam. Some cases sodium amalgam also they will use. Okay, zinc amalgam concentrated HCl. Okay, so here mechanism if you take it is complex mechanism. Here the actual reduction occurs by a complex mechanism on the surface of zinc. Surface of zinc. Okay, so this is Clemmensen reduction. This one is Clemmensen reduction. And Wolff-Kishner reduction, if you take in, here also carbonyl group, this group is converted into alkane CH2 here, methylene group. But in that middle, hydrazone will form. First, hydrazine. This is what is that? Hydrazine. This hydrazine first react with keto group or aldehyde group, hydrazone will get in. That hydrazone, when it is reacting with base, alcoholic KOH or potassium tertiary butoxide, potassium tertiary butoxide, like the strong base, if we use there, what we are getting alkyl benzenes. That means a carbonyl group is converted into alkene. Carbonyl group is converted into alkane. That reaction is called Wolff-Kishner reduction. That reaction is called Wolff-Kishner reduction. Here, so propiohexone. Okay, what is that? Propionone. This one is converted into what is that? Hydrazone, N-propyl benzene. We got it. And propyl benzene. Now see here, if you take it here, that here hexanone, cyclohexanone, when it is react with hydrazine, so hydrazone, we got it. In the presence of potassium tertiary butoxide and dimethyl sulfoxide, it is solvent, dimethyl sulfoxide. There, what's happening here? That case, this hydrazone is converted into this hydrogen is converted into, so what is that, alkane, like this. Here mechanism is there. Here we'll see that mechanism. So here aldehydes, ketones in the presence of hydrazine basic medium means OH group or potassium tetrohydroxide and ethylene glycol. If you use that, keto group is converted into methylene group. So mechanism, if you see Wolff-Kishner reduction, okay, mechanism, if you see here, what is happening? The first, keto group and hydrazine, when those two reacting each other, hydrazone we got it. Like that, hydrazone we got it. So after getting that hydrazone, here nitrogen is combining with the two hydrogens there. Those are having slightly positive charge. That means those are having slightly positive charge due to that nitrogen is more electronegative atom. So in the presence of base, so the base is giving electrons to hydrogen. Why means due to positive charge means slightly acidic nature, that's showing that hydrogen is showing. It is showing slightly acidic nature here, this one. So it is giving OH group giving electrons to H plus ion. So what's happening here? There H2 is forming, like that H2O is coming out. So there nitrogen got here negative charge. Nitrogen got negative charge. Now between these two double bond is there here. Now these electrons are moving toward this side. That time carbon, this carbon got negative charge. This nitrogen got positive. To this positive charged nitrogen atom, this nitrogen, negative charged nitrogen atom gave electrons. So that case, what happened between carbon and nitrogen, whatever double bond is there, it's converted into single bond and carbon got negative charge. And between nitrogen and nitrogen, single bond is there, so that one is converted into double bond. Okay, so now carbon, when it is getting negative charge, it shows more basic nature. It attracts a proton. So already here water formed from that water. Now this negative charged nitrogen atom attracting proton. So that's why this negative charged carbon, okay, donating proton from hydrogen, from water, and it's giving electrons to like this. So this way, once again OH minus is formed, and this hydrogen attached to this carbon. So what you got there, like that, we got it here, this group. And once again, OH minus attacking nitrogen combined with hydrogen. This is having slightly acidic nature. Now this is attacking once again this. So this hydrogen is giving electrons to this nitrogen and hydrogen getting positive charge. So this negative charge between these water is forming. So H2O is coming out. Hmm. So now here what happened? Negative charge nitrogen atom. Negative charge nitrogen atom. Understand? So now between carbon and nitrogen, one single bond is there. That bond undergoing homolytic cleavage and electrons are moving towards carbon. These electrons are moving towards carbon. So carbon getting negative charge, this nitrogen got positive charge. So this nitrogen positive charge, this nitrogen negative charge. Between those two, what is happening? One more new pi bond is forming. Already one sigma bond, pi bond is there. One more bond is forming. That means what's happening here? Nitrogen gas is liberated. Like that, what happened then? Carbon got negative charge. This carbon got negative charge. That negative charge carbon, when it is having negative charge, it shows more basic nature. So it accepts proton from water. So it is accepting proton from water, and these electrons are moving towards oxygen atom side. That way, this hydrogen also combining with this carbon, and like that, CH minus is converted into CH2 and plus OH minus you are getting plus OH. This is the mechanism of Wolff-Kishner reduction. This is the mechanism of Wolff-Kishner reduction. This way we can prepare aldehydes and ketones from okay, we can prepare alkanes from aldehydes and ketones. Okay, here mostly that so which is more sensitive carbonyl group towards acid. That case we don't use Okay, okay, zinc amalgam, what is that? Clemmensen reduction. Example, if you take in, okay, this compound, if you take it C1s, here one group is there here, this one, this compound, here COCH3. Okay, it's not benzene here. COCH3 is not benzene, here OH group is there. So, if we use here zinc amalgam concentrated HCl, what I will get it means here that OH will be replaced and OH is replaced by Cl and there I will get it CH2CH3 like this I'm getting. Here what's happening? This OH group is replaced by Cl. OH group is replaced by Cl. That means it is more sensitive towards acid. But actually, what I require without disturbing OH, just that CO should be converted to CH2. That case, which one I have to use here? Okay, I have to use hydrazine, Wolff-Kishner reduction. When I'm using hydrazine base and ethylene glycol, hydrogen base and ethylene glycol if I use, what will happen then? So that OH it won't be replaced by hmm, okay, basically that OH won't be replaced by base and just CO group is converted into CH2 like that. So okay, so that's why in this reaction, which is more favor means here this is okay, Wolff-Kishner reduction is more favor to convert carbonyl group to alkane, but not Clemmensen reduction. Okay, students, understand? So this one you can take it. And next, alkene from alkenes. From alkenes, here very famous reaction. One famous reaction is there here. That one is Sebastian-Sanderens reaction. Sebastian-Sanderens reaction. What is Sebastian-Sanderens reaction means? Alkenes converted into. Okay, here alkenes converted into alkanes. Alkenes converted into alkane. Not only alkenes here, alkenes are alkynes converted into alkanes in the presence of nickel, palladium, platinum. Nickel, palladium, platinum, hydrogen gas. So those reactions are called Sebastian-Sanderens reaction. In this reaction, specialty is what is the cis manner. That means addition of hydrogen to double bonded carbon in syn manner. Syn manner meaning from same side it will be added. Hydrogens will be added. So like that, addition of hydrogen to alkene, that is syn addition or cis addition. So same side will be added. Here, see once first, ethene is given here. Okay, it is also called ethylene. This ethylene, when it is undergoing a reduction in the presence of nickel, there what you got it there here, ethane we got it. What you got it? Ethane we are getting. So now a double bonded substance is there. It is cis substance. This is what is that here? Cis form. So this cis form, why is it is cis form? Identical groups, same side are there. Deuterium, deuterium, same side. And alkyl group, same side are there. So identical groups, same side are there means cis form. Now, cis form when it is undergoing syn addition. This addition is what is it here? Syn addition. Identical groups when those are undergoing. Okay, so cis form when it is undergoing syn addition. Syn addition, what's happening there? Which compound will get me? Meso compound will get it. What will get it? Meso compound. Meso compound means what is that? Here chiral carbon will be there. Yeah, this is chiral carbon, chiral carbon. But internal compensation will be there. Okay, so meso compound, internal compensation. Internal compensation will be there. Due to internal compensation, this one is optically inactive. Optically inactive. Okay, like that meso compound we are getting. And next, transform if we take it. So trans, the trans substance if you take it. So in the transform, when it is undergoing syn addition, so that means hydrogens added to alkene is always syn addition. So this is syn addition. When syn addition is taking place, when syn addition is taking place, there what we can get in trans when it's under syn addition, there we can get it racemic mixture. One is a dextro form we can get in, another one is levo form. 1:1 ratio. 1:1 ratio, dextro form and levo form we are getting. When we are getting that ratio, 1:1 ratio, that one is called, what we call that one here? That is called racemic mixture. That one is called racemic mixture. Like that, racemic mixture we are getting. Racemic mixture is, what is that? In this, it is also optically inactive. Why it is optically inactive? Due to external compensation. External, due to external compensation, it is optically inactive. Optically inactive. Okay, students. So like this you will get it. Racemic mixture, external compensation. Dextro compound having clockwise rotation, levo compound having anti-clockwise rotation. Both are in 1:1 ratio in that mixture. What will happen? Dextro anti-rotation, sorry, dextro clockwise rotation is cancelled by levo anti-clockwise rotation. That's why that one is called external compensation, optically inactive. This point is very important. Okay, and hydrogenation of alkene. This point, check it one here. So if you take it this reaction is exothermic. Heat of hydrogenation depends upon number of alpha hydrogens. It's very important, this point also. Here, number of, okay, stability is directly proportional to stability is directly proportional to number of alpha hydrogens. Number of alpha hydrogens. So when number of alpha hydrogens increases, stability increases. The stability increases, heat of hydrogenation decreases. So heat of hydrogenation is inversely proportional. Heat of hydrogenation is inversely proportional to number of alpha hydrogens. That means alkene which is having less number of alpha hydrogens, that is more reactive, that alkene having more alpha hydro, that alkene having, okay, more heat of hydrogenation. Based on that, here, okay, CH2 double bond CH2, it is more reactive than okay, CH3 twice C double bond CH3 twice. It is having 12 alpha hydrogens. Here nil, no alpha hydrogens. No alpha hydrogens. Okay, this is more reactive. This is less reactive. Hmm. So heat of hydrogenation is more for this less. Okay, students, like that you can take it. So this is about substrate-Sandrens reaction. This is about substrate-Sandrens reaction. Okay, cis manner this addition takes place. Next, hydroboration. Hydroboration followed proteolysis. Okay, first hydroboration. Here, little bit it follows just what is that anti-Markovnikov rule. Okay, hydroboration means anti-Markovnikov rule. Anti-Markovnikov's rule. So in this case, what's happening here for CA rod? So in this here, if you take it here, what's happening in this? Here CH2 double bond CH2 is there. So these pi electrons are moving towards one of the double bonded carbon. So in that boron hydrogen, if you take it, boron third A group element electron deficient. That's it gets positive charge. It's getting negative charge. So when these pi electrons are moving toward this carbon, What's happening? This carbon also getting negative charge. This one is getting positive charge. So like that, here negative charge, here positive charge. So this way, what's happening then? So this negative charge combined with this positive charge combined with this, like that between those one transition state we can get. So what's happening? Like this. So this is transition state, like the transition state we are getting. So this between this, like this, one transition state will get it. After getting the transition state, so transition state means intermediate state. It will undergo dissociation. It's undergoing dissociation. So there, what you can get it there. So this bond like this. So this bond is undergoing this. So like that, CH3 bond CH2, bond CH2, bond BH2, got it. Bond BH2. Okay. So after getting this BH2, proteolysis. So here proteolysis follow proteolysis means, so what will happen? This is undergoing dissociation and it's getting, it's the alkane, we got it. So instead of that, hydroboration continuously takes place. What will happen? See once. It is unsymmetrical alkene. This unsymmetrical alkene, when it is undergoing hydroboration, there you can get it. So like the transition state, after that transition state, it will undergo dissociation and it's giving like this alkyl boron complex. So this one you got it. And here one hydrogen is replaced by one alkyl group. Like that, here two more hydrogens are there. Those two hydrogens also replaced by this alkene. So when that alkene hydrogen is replaced by alkene, that alkene is converted into alkyl. So like that, how this alkene. Okay, so this hydrogen is replaced by alkene. What happened then? Alkene is converted into alkane. So same way, here also these two hydrogens are replaced by this alkene. That case, what will happen? These hydrogens are moving towards, okay, this carbon atom, boron moving towards this carbon atom. Like that, trialkyl boron, we got it. What we got it? Trialkyl boron. This after getting the trialkyl boron in the presence of hydrogen peroxide and base. So, sorry, in the presence of proteolysis we are taking, in the presence of so water and proton, in the presence of water and proton, what's happening? That hydrogen is, that boron is replaced by H plus like this. So we got it like this. You got it? So this one. So same thing we are using in that hydroboration. So hydroboration followed by proteolysis. So same like this reaction we'll use for preparation of alcohols also. Their hydrogen peroxide base we'll use. Hydrogen peroxide and base. Okay, students. So this. And see once, so already we discussed this one, Sabastide-Sanders reaction. There previously, what we discussed for alkenes we discussed. Now this is from alkynes. This is from alkynes. So this alkyne, okay, in that Sabastide-Sanders reaction, platinum, palladium, nickel, methyl alcohol. What is the use means? It's like what is that solvent. Hmm. So first alkene is converted into alkyne is converted into alkene. That alkene one is once again when it is undergoing hydrogenation, there you can get alkene. What will get it? Alkene. So like that, alkynes, alkynes converted into alkene. Next, alkenes converted into alkanes. Okay, this reaction is called Sabastide-Sanders reaction. Sabastide-Sanders reaction. Nickel, palladium, platinum will use. Okay, students. Next, from alkyl halides. From alkyl halides, whenever you are using. From alkyl halides, if you take in, so by reduction. from alkyl halides by reduction. That means alkyl halides means what are those? Alkyl group is combined with alkyl halide. Alkyl group is combined with halogen. Like this, alkyl group is combined with halide. When alkyl halide is reduced with, when alkyl halide is reduced with zinc copper couple and alkyl halide and sodium and ethyl alcohol and sodium amalgam and water and lithium aluminum hydride. These all are good reducing agents. These all are good reducing agents. These are when those are reacting with okay, what is that? These alkyl halides when those are reacting, these reagents, reducing agent, zinc copper couple, ethyl alcohol, sodium ethyl alcohol, sodium amalgam water, lithium aluminum hydride. In that case, nascent hydrogen atom coming out. There we will get it alkane plus alkyl. Okay, that means hydrogen halides. Like that, we are getting the alkanes. Okay, students. So from alkyl. So like this, you can get it. Like that, we can get in. So here some reactions. So here halide X is replaced with hydrogen. Here CH4, we got it CH4. Okay, students. Next, Wurtz reaction. Next one is what is that? Wurtz reaction. Wurtz reaction, very famous reaction. Okay, so many cases we discussed this one. Here, Wurtz reaction is what is that? It is also reaction with alkyl halide. Alkyl halides, when those are reactive with sodium in the presence of dry ether, we will get higher alkanes. Higher alkanes. But very, very important. So it is only for to prepare symmetrical alkanes. Symmetrical alkanes. Why symmetrical alkanes means? So symmetrical alkanes means then only we will get high percentage, high yield of okay, alkanes will get in symmetrical alkanes. Otherwise, very less percentage of okay, unsymmetrical. That means whenever you're taking alkyl halides, we are easily prepare here symmetrical alkenes. We can easily prepare here symmetrical alkenes. Okay, I will explain clearly once listen. So in this alkyl halide, alkyl halide in the presence of sodium metal, what's happening? The sodium taking those two halogens. So like the sodium halide plus here alkanes. Here two mechanisms are there. One is heterolytic mechanism, ions based on ions formation. Okay, one is ionic, another one is free radicals mechanism. Both I will explain. Okay, so here C1s. So mechanisms, if you see here, what is there here? Via organometallic compound. Via organometallic compound. So here, very, very important, mostly we have to use dry ether. What is the use of dry ether? It is the solvent. And dry ether, why we are calling that is dry ether means without water we have to take it. Without water, any little amount of water is there means that water react with sodium metal. That's why we must take the dry ether. That solvent shows more inert nature. That solvent shows more inert nature. Here, ethyl bromide and sodium metal is given. So mechanism how we'll get in. So ethyl bromide means two sodium metals if you take it. So ethyl bromide bond Br and sodium metals. Two sodium metals if you take it. What is happening mean here homolytic cleavage takes place. What will happen here? Sorry, not homolytic here. Heterolytic cleavage. Heterolytic cleavage takes place. So that means it's getting negative charge. This is getting positive charge. So after getting negative and positive charges, so these two sodium atoms donating electrons to two sodium atoms. One sodium atom can donate one electron. Two sodium atoms donate two electrons. So these two sodium atoms donating electrons to this one. When those two sodium atoms donating electrons to ethyl Okay, ethyl carbocation converted into carbanion, CH3 minus. CH3 minus and plus Br minus, you got it. CH3 minus C2H5 minus, you got it. Br minus. Why? How we got C2H5 minus? So Y means positive charge. One sodium donating one electron. So positive charge is becoming neutral. One more electron if you donate in, it gets negative charge. Now here those two sodium atoms so became Na plus. So C2H5 Na plus and Na plus Br minus. Like that we got it sodium bromide and sodium ethoxide. This is organometallic compound. This is what is that? Organometallic compound. This organometallic compound. Okay, this organometallic compound once again when it is reacting with ethyl bromide. So C2H5 minus Na plus and once again when it is reactive with ethyl bromide. So here what's happening? Heterolytic cleavage. Here negative charge, here positive charge will get in. So what will happen? This Na plus is combined with Br minus. So what you can get? Sodium bromide. And remaining things, what are those here? C2H5 minus and C2H5 plus. Okay, CTH5 minus CTH5 plus you will get in. So when those two combine together, there you are getting C2H5 bond C2H5. Like that, you will get there butane you are getting. What you got it? Butane. Understand? So this is example for what is that here? Organocarbon heterolytic cleavage. Okay, heterolytic mechanism. So that one. And free radical mechanism is it's very simple. Free radical mechanism means how we'll take it here. So here free radical mechanism here. Hmm, it is here. What is that? Heterolytic cleavage. Here what happened? Heterolytic cleavage happened. In this case, homolytic cleavage. Homolytic cleavage. So when you take it there heterolytic cleavage and homolytic cleavage, that homolytic cleavage means two free radicals you got it. So like that what you are getting then C2H5 radical plus bromide radical you got it. And now this C2H5 radicals, two if you take in, two C2H5 radical, two Br radicals. So to this Br radical, sodium metal is giving electron. So Na plus Br minus. When those two combine together, sodium bromide. Why means sodium metal donating electrons to this one. So sodium metal when it is donated electron to Br radical, there you got it Br minus Na plus. Na plus Br minus those two combine together and giving sodium bromide. And C2H5 radical those two combine together. From this you got in what is that butane. What you got it? Butane. Okay, so like this we are preparing alkanes from this compound. Alkanes from this compound. It is which reaction? One is what is that heterolytic cleavage, another one is homolytic cleavage. Homolytic cleavage means free radical mechanism, and heterolytic cleavage means okay, what is that organometallic compound? Okay, students, thank you.